guys, I want to shoot some more videos. We introduced conversion with the plug flow reactor, but I'd like to show you guys it's also true if you do it for the continuous stir tank reactor and the batch reactor. So I'm going to show you how to do the batch reactor first and how to get conversion into your equations. So we saw that we had, here's our box, right, our batch reactor. We saw in minus out plus gen equals accumulation. And like we haven't seen in a minute, is that these two are 0 and accumulation still exists. Then generation term, if you can guess it, is RA times V, right? It's equal to dNA, I love saying that, dt, just like this. But how do we get conversion into this equation? It's not too hard. It's something you actually seen too. So here's what we do. We take RAV, we're going to leave that alone for a minute, and we're going to, oh, I'm sorry, no we're not. RA is equal to dNA, just like before, dt. Let's divide the 1 over V. Now the trick was way back when that you could put the V into the derivative because it's constant. So then RA will become dNA over V, moved it into the derivative, dirt. So we moved it in. So this could be rewritten as like this, dCA dt. Okay. Now I can see one place we could put the conversion in already. Let me show you. RA is equal to D. Now CA is also equal to CAO times 1 minus X from this equation. That was from the plug flow case. I explained that in a video prior to this. But basically this conversion gives you the amount of A that disappears per molar A fed, and when you do the 1 minus X case instead of CAO times X, but CAO times 1 minus X, it gives you the amount of A, or concentration of A that's left. Okay, so we have this one, we have dt. So let's pull some constants out. Like, if we could put constants into a derivative, we can pull them out. And I mean it like this. Just like this. Okay. Now, what the heck are we looking at with that? It does look a little confusing. It's actually not. dt, like this, right? So let's split this up, right? We have d of the number 1 over dt minus d of x over d of t. That's going to go to 0 because it's just a number. And we're left with this. So then what you're left over with is RA is equal to CA. Sorry, this should have been O. That's why we pulled it out, right? CAO times negative dx. Sorry, like this. dx dt. Now let's pull that negative sign out, put it into the RA. Move the negative to the other side. And then voila, we're done. Now, when you get your conversion, or not conversion, but reaction rate, you're going to get them in terms of concentrations like this, right? So let's take the case where we're given a first order. We plug that in for negative RA, like this, see? And now we're not going to use CA, we're going to use our little conversion trick again, just like this. And we're going to plug that in, like this. Okay, so it's CAO dx dt. Now CAO's canceled, see what happened? So now what we're left over with is K times d of t is going to be equal to d of x over 1 minus x. So now integration is possible, right? So we can say, okay, well that's k of t is equal to, and we've already determined that this is the answer to this, 1 over 1 minus x, ln, for that integral. Really looking at it like this, 0 to x, 0 to t. Okay. Now, let's solve for x. Let's not stop here. We can solve for x. X equals to a function of t. So take the exponential of both sides, ekt, is going to be equal to 1 over 1 minus x, right? So we flip both sides. So instead of saying 1 over e to the kt, we say e to the negative kt is equal to 1 minus x. Let's add x to the other side and subtract e to the right side. So swap them out, per se. Hey, look, we know the conversion is a function of time inside of a batch reactor. Okay, so for continuous stirred tank reactors, how do we involve conversion with that? Well, let's take this box for instance. Right, it comes in, it leaves, and we said that the concentration inside the continuous stirred tank reactor is going to be well mixed, was the assumption. Meaning the concentration inside the reactor is the same as that leaving on the leaving stream. We call that CA exit, I believe. CAO. So we have in minus out, like this, plus gen equals accumulation. Now we're going to say steady state, kind of like the PFR and the PBR, but we don't have any derivative terms here because of this being like that. So then what we say is, okay, well, FAO goes in, minus FA that comes out, plus RAV, which is the volume, equals 0. Now, we did the incremental step theorem in the PFR. That's what we did. We're not going to use that this time. We're simply just going to do this. Just the definition we're used to working with, right? That's what we're going to do in regards to the CSTR. So the analysis becomes real easy. We always want to usually solve for V because that's what they call sizing a reactor. So in this case, FAO minus plus, let me do this right. Make sure I do it right. So FAO minus FAO, I'm distributing FAO into 1 minus X plus FAOX plus RAV equals 0. Okay, we're almost there. Okay. So V is going to be equal to negative FAO to the other side, but I'm going to say positive FAO X over negative RA. If you move it for V, you'll find that this is your solution. Okay, so that's how you introduce conversion into CSTR. All right, perfect. I'll see you guys in the next video. We'll discuss the Dam-Kohler number. All right, have a good one.